Good day everyone, I am Edric Luis G. Ato and today I'll be teaching CALENG1 or Differential Calculus, LQ number 2. Specifically, a variable raised to variable derivatives. So, first, what does a variable raised to a variable derivative look like? Well, there are three cases on how to see them. The first is when there's a variable in the base and then a variable in the exponent. That's the case 1. Case 2 would be if there is an expression for the base, like x plus 3, and a single variable as the exponent. In the third case, or the more general case, is if there is an expression as the base and another expression as the exponent. These expressions may be equal to each other, but both of them should not be just a constant. So any polynomial or any expression rather, just as long as it's not a constant. Neither of them are constants. How come neither of them should be constants? Because if we, for example, have a constant at the base and then an expression for the exponent, to get the derivative of this, we are going to use the formula for a raised to x. So this would be 2 raised to the exponent, x plus 3, then ln2, and then the derivative of x plus 3, which is equal to 1. So it's just simply 2 raised to x plus 3 ln2. How about if we have a constant as the exponent? So for example, x plus 3 squared. Well, we just simply use a chain rule here. So both of these are not considered variable raised to variable or expression raised to an expression problems. So for this, let's generalize, let's make it expression raised to expression, not just a variable raised to a variable. Now, this is kind of yucky. See, because we have a variable in the base and a variable at the exponent. Now, there are two ways for you to solve the derivative of that. And I'll show you both ways. But for both ways, they start with the same thing. We take the natural logarithm of both sides. Let's take x plus 3 raised to x minus 2 for an example. We take the natural logarithm for both sides. Or actually, let's use x raised to x for a simpler example first. X raised to x. Now, take note. If you have a logarithm of b with base a raised to n, that would be equal to n times the logarithm of b with base a. So we can just shift the exponent to the front. So here it's the same thing. We shift the exponent to the front. So this would become x ln x. So here we have method 1, and let's do method 2 on the right side. Method 1 is by using implicit differentiation. Oh, sorry, wrong spelling. Implicit differentiation. And method 2 is using the chain rule. So, let's first use implicit differentiation. Let's differentiate both sides. D over dx of ln y equals d over dx of x ln x. Since y is a y is a function of x, let's use chain rule here. What is the derivative of ln y? That's 1 over y. And then what's the derivative of y? That's dy over dx. That's equal to, we use the multiplication rule here. So x, derivative of x, that's 1 times ln x, plus x times the derivative of ln x, which is 1 over x. Here we can simplify this to be equal to 1. So it would be ln x plus 1. We multiply both sides by y to just keep dy over dx. So this becomes y times the quantity ln x plus 1. But we already know that y is equal to x raised to x. So we can substitute y. This becomes x raised to x times the quantity ln x plus 1. And that's the final answer. Whether you want to distribute the x raised to x to both terms, it's up to you. Or it depends on your prof. For method 2, let's use a chain rule. But let's manipulate the given further. We now know that ln y is equal to x ln x. Let's raise both sides of the equation to from e. So it becomes e raised to ln y, that's simply equal to y, equal to e raised to x ln x. Let's not simplify this yet. Why? Because we are now going to get the derivative of this. This becomes dy over dx. That's equal to the derivative of e raised to x ln x. That's e raised to x ln x times the derivative of the exponent. So derivative of x ln x. So we're going to be using the multiplication rule here. Derivative of x, that's 1 multiplied by ln x. Then derivative of ln x, that's 1 over x multiplied by x, or just simply 1. Now we can simplify this. This is now equal to e raised to ln x raised to x times ln x plus 1. E raised to ln x is just simply x, so it's x raised to x times ln x plus 1. And as you can see, the answer that we got is the same. Let's have a second example. Y equals x plus 3 raised to x. Y equals x plus 3 raised to x. Let's try to use method 2, the chain rule, so that we don't need to take the natural logarithm of y. We could just say that's equal to e raised to ln x plus 3 raised to x, or simply e raised to x ln x plus 3. Then we use a chain rule. Dy over dx is equal to, copy the expression, then multiply it by the derivative of the exponent. This will get ln x plus 3 plus x over x plus 3 times the derivative of x plus 3, which is 1. So we will get x plus 3 raised to x times the quantity ln x plus 3 plus x over x plus 3. Oops. That is the final answer. Last, let's use the given of y equals x plus 3 raised to x minus 2. Y equals x plus 3 raised to x minus 2. This time, let's use implicit differentiation for this. So this would be 1 over y times dy over dx is equal to This now becomes x minus 2 ln x plus 3. Okay? Derivative of the first term, so that's just equal to 1. Times the second term, so it's ln x plus 3. Then add the first term. Then the derivative of the second term. So that would be equal to ln x plus 3 plus x minus 2 over x plus 3. Multiplying both sides by y, we would get y times the quantity ln x plus 3 plus x minus 2 over x plus 3. Substituting y, this now becomes x plus 3 raised to x minus 2 times the quantity ln x plus 3 plus x minus 2 over x plus 3. That's the final answer. Now, if you guys can see a pattern here, okay, there's actually a pattern here. So, let's make it more general. Let's say y equals u raised to v, where u and v are also functions of x. So, we can say that it's going to be ln y is equal to v ln u. Then if we use implicit differentiation, 1 over y times the quantity dy over dx equals dv over dx ln u plus 1 over u times v du over dx. So dy over dx is equal to y times the quantity ln u times the derivative of v with respect to x plus v over u times the derivative of u, that's supposed to be u, not v, the derivative of u with respect to x. That's the general solution. But you don't need to memorize this. You just need some practice for using implicit differentiation and the chain rule. And always remember, if you see an expression raised to an expression, you can use the natural logarithm for both sides so that all of them will now be products. Although this method will also work on others. So let's say, for example, y equals 2 raised to x plus 3. If we take the ln on both sides, ln y is equal to x plus 3 ln 2. If we use implicit differentiation, what we're going to have is dy over dx is equal to y ln 2, which we know that y is equal to 2 raised to x plus 3 and then ln 2, which is the same as what we have earlier. Now let's try y equals x plus 3 quantity squared. if we take the natural logarithm on both sides, it becomes ln y equals 2 ln x plus 3. Then if we solve for this, we will get dy over dx equals 2y over x plus 3, which is equal to 2 times x plus 3 quantity squared over x plus 3, which is simply 2 times x plus 3 or 2x plus 6, which is what we got earlier as well. Now, let's try something a bit harder. Let's say 4 raised to x squared. Okay? For us to do that, we can use ln y is equal to x squared ln 4. Okay? Although simply this is just essentially a number raised to a variable. So we can just use 4x squared times 2x times ln 4. That would be the final answer there. So let's check. So x squared, derivative of x squared is 2x. Then copy this. Then that's equal to 0. So this is 2x ln 4. dy over dx would now be equal to 2xy ln 4 or 2x times 4 raised to x squared ln 4, which is the same thing that we will get if we use the number raised to a variable. And let's try something a bit harder. Let's say x squared plus 3x plus 1 raised to x to the 5th minus 2x to the 4th. Okay. Now, we would do ln y is equal to x to the 5th minus 2x to the 4th ln x squared plus 3x plus 1. Now, this looks hard at first, but don't worry because this is just multiplication rule and chain rule. So, let's use implicit differentiation for this because this is a bit long. This now becomes 1 over y times dy over dx. That's equal to the derivative of the first term. That is 5x to the 4th minus 8x cubed. And then copy the second term. Plus, copy the first term. Oops. It should be x to the 5th minus 2x to the 4th. Then multiply by the derivative of the second term. And then we get dy over dx is equal to, let's substitute y directly. So this is x squared plus 3x plus 1 raised to x to the 5th minus 2x to the 4th times, let's make that a square brace because it's a bit long, 5x to the 4th minus 8x cubed ln x squared plus 3x plus 1 plus, we can distribute x to the 5th minus 2x to the 4th times 2x plus 3. This becomes 2x to the 6th minus 2x to the 5th plus 3x to the 5th. Oh, sorry, minus 4x to the 5th plus 3x to the 5th. That becomes minus x to the 5th, then minus 6x to the 4th. All over x squared plus 3x plus 1. And that's the final answer. Now, as you can see here, there are actually no terms to be simplified. But if there are terms that are simplifiable, your prof might appreciate you simplifying or combining like terms. And that marks the end of the variable raised to a variable topic. If you learned something, please leave a like and comment down below. So thank you so much for watching. You may also avail syntax tutorials by scanning the QR code flashed on your screens right now. Once again, I am Edric Luis G. Ato from Syntax, paving your way to excellence. Thank you for watching.